All right, so we have this problem, 1.7 times 10 to the fourth atoms. And we need to figure out how many moles that would be. Okay. Now the cool thing about moles is it doesn't matter if they're atoms or molecules. Every mole is 6.02 times 10 to the 23rd particles, whatever those particles are. So we set up what we know as a fraction, and then we're going to multiply that by a conversion factor. Now we need atoms on the bottom of that conversion factor so they cancel out. So we know that 1 mole is 6.02 times 10 to the 23rd atoms. So that's our conversion factor. So we multiply across the top, and we're just multiplying by 1, so it stays the same except for the atoms canceling out. And then we multiply across the bottom. Again, it's by 1, so it stays the same except the moles canceled out. Then we divide, and once we divide, we get 0.28 times 10 to the negative ninth, but that is not in scientific notation. So we're going to change that to 2.8 times 10 to the negative ninth. Okay, and that's going to be moles, and that is our answer. All right, so here we have another problem. This time we're starting with moles of gold, and we need to figure out how many atoms we're going to get out of this. So this is the reverse of what we already did. So we're going to do it the same way, except our conversion factor will be flipped. All right, so we have 24 moles to start with. That means moles have to be on the bottom of our conversion factor, because we want those to cancel out. And we know that 1 mole is equal to 6.02 times 10 to the 23rd particles. Okay. All right, so we cross out our moles because they've canceled out, and then we do some math. And again, our initial answer is not in scientific notation, so we have to put it in scientific notation. We multiplied the numbers, and then we added the superscripts or the exponents. All right, so here we had to find the molar mass of each thing. Now sodium, we just look at the periodic table, it's 22.9 grams per mole. For N2, we have to multiply that by the 14.01 from the periodic table by 2 to get the molar mass. For platinum chloride, ionic substance, we're going to have to find the mass for each element. Platinum, there's only one atom, so we just write down 195.08. For chlorine, each chlorine atom is 35.45, but there are 6 atoms in each formula. So we have to multiply that by 6. And then we're going to add everything together. Okay. So click on the keyboard, and we get 407.78 as the molar mass because we had to add everything together. All right, so moles to mass. So we have 0.5 moles of carbon. We want to know how many grams that would be. So the first thing we do is we look at the periodic table, and we find that 1 mole of carbon equals 12.01 grams per mole. Okay, so that's our conversion factor. So we say 0.45 moles of carbon over 1 times 12.01 grams over 1 mole. We want moles on the bottom because we want those to cancel out. All right, so then we multiply across the top, multiply across the bottom, and divide. So in this case, we're going to say 0.45 times 12.01, and that gives us 5.40 grams. So if you had 0.45 moles of carbon would have a mass of 5.4 grams of carbon. Okay? Now, that makes sense because if 1 mole has a mass of 12, then half a mole would be about 6 grams. And so this is less than a half, so that makes sense. Story checks out. So if we want to do grams to moles, let's say we have 153 grams of phosphorus pentoxide, okay? And we want to know how many moles that would be. So we're going to take, the first thing we need to do is find the molar mass of diphosphorus pentoxide. So we look up phosphorus, and phosphorus has a mass of 30.97. One does, but we got to multiply that by 2 because there's 2 atoms in each molecule. And then oxygen, okay, is 16.00, but we have to multiply that by 5. All right, so we do some quick math. All right, so now we have the mass of phosphorus and oxygen. So we're going to add those together. And so the molar mass of diphosphorus pentoxide is 141.94. Okay? Now, that's the first part. That's like the background calculations. We still have to answer the actual question. So we know that we have 153 grams, right, of diphosphorus pentoxide. We need to convert that to moles. So we want moles on top, grams on the bottom. Grams cancel out. 1 mole of diphosphorus pentoxide is 141.94 grams. All right, so we multiply across the top, we get 153 moles. Multiply across the bottom, we get 141.94. We don't get grams because they canceled out. So then we divide. All right, so for our final answer, we get 1.08 moles. And this makes sense because 1 mole is 141 grams. We have 153 grams. So we're just a little bit over 1 mole. So this makes sense, okay? Now, we just found out that 153 grams of diphosphorus pentoxide is equal to 1.08 moles of diphosphorus pentoxide. Now, we can take this a step further and we can figure out the number of molecules in this, okay? So, molecules, okay? How many molecules are there? Well, we know that 1.08 moles, okay, times, we'll put 1 mole down here because we want those things to cancel out. And up here, we're going to put 6.02 times 10 to the 23rd because any mole has that many particles in it. It doesn't matter if they're molecules or atoms or eggs. If you have a mole of something, you have 6.02 times 10 to the 23rd. Just like if you have a dozen of something, you have 12 of them. Okay? So our moles are going to cancel, multiply across the top, multiply across the bottom, and we're going to be left with 1.08 times 6.02. That gives me 6.50 times 10 to the 23rd. Okay? So if you have 153 grams of diphosphorus pentoxide, that will be equal to 1.08 moles of diphosphorus pentoxide. And if you have that, you also have 6.5 times 10 to the 23rd molecules of diphosphorus pentoxide. Okay, all three of those are equivalent. Okay, this is like, well, I don't have a metaphor, but those are all equivalent. All right. Now, if everything is at STP, standard temperature and pressure, then we know that 1 mole of a gas, doesn't matter what gas it is, if it is at standard temperature and pressure, 1 mole of a gas is 22.4 liters. We know this experimentally. We have shown this over and over again. Okay? So if we have 839 liters of argon, okay, how many moles would that be? All right, so we have 839 liters over 1 times a conversion factor. Now we know we need liters down here, and we want moles, so let's put moles up here. Liters cancel out. We know that 1 mole is 22.4 liters. Okay. This is just something you need to stick in your brain. All right, so we're going to say, we're going to multiply across the top, multiply across the bottom. We have 839 moles divided by 22.4, because the liters canceled out. So 839 divided by 22.4 is going to be 37 I'm going to say 5 moles. Okay? So that's it. If you want to go the other way, okay, then you could say, all right, let's say we had 26.4 moles of sulfur gas, okay, and we want to know how many liters that will be. And remember, liters is a unit of volume. So we're going to say 26.4 moles over 1. We'll multiply that by our conversion factor. We know we need moles down here. 1 mole is 22.4 liters. Moles cancel. So we're going to say 26.4 times 22.4, and we get 591.4. Nope, just the 4, I think. Liters. Okay? So that's how you convert from moles to liters and liters to moles. Now, we could convert from liters to moles to grams, and we can convert from grams to moles to liters. That's the mole highway that is mentioned in your book. All right, so now we're being asked to do percent composition. So if you're given something like R, that's RBI, okay, rubidium iodide. So the first thing you gotta do is find the molar mass of rubidium iodide. So we find rubidium, and Rb has a mass of 85.47. Iodine has a mass of 126.90. So we're going to add those together. This is a 1-to-1 ratio, so we just add them together just like they are. So 126.90 plus 85.47. Okay, so that's going to give us 212.37 as the molar mass, grams per mole of rubidium iodide. Okay, now what we've got to do is figure out what percentage rubidium is of that mass. and what percentage iodine is of that mass. All right, so for rubidium, we're just going to say 85.47 divided by 212.37. All right, so 85.47 divided by 212.37, and that gives you 40. Well, I skipped a step. Let me back up a little bit. So times 100% equals, so 40.2, right, percent. So 40% of this mass is rubidium. And then let's see here. So iodine would be 126.90 divided by 212.37 times 100% equals. Now we would assume that this should be around 60% because this is around 40. So 126.90 divided by 212.37. So that gives us 59.8%. Okay, so there you go. That's how you do percent composition of a compound. All right, so let's say we want to find the density of a gas. Okay, remember that 1 mole at STP is 22.4 liters for gases. This is only going to work with gases. Okay. Now let's say we have H2S as a gas, and we want to find the density of it. Okay, so we know that the volume, well, we know that density is mass divided by volume, right? And we're talking about 1 mole. So we know that the volume, okay, is 22.4 liters. We know that the mass, all right, of 1 mole, we're going to look at our periodic table. We know that hydrogen is 1.008, but it's H2, so we have to multiply that by 2. We know that sulfur is 32.07. All right, so then we're going to add all that together, and we're going to say 2 times 1.008, that's 2.016, or 2.016. We're going to add to that 32.07, and so the mass is equal to 34.09. Okay, grams per mole. That's the molar mass. All right, so we now have the volume of 1 mole. We have the mass of 1 mole. So we substitute in, and density is equal to 34.09 divided by 22.4. Don't forget your units. Okay, so 34.09 divided by 22.4 is going to be 1.5. That's it. 1.5 grams per liter. So then that's the density. Okay. If you needed to go the other way, if you had the density and you had to calculate the mass, the molar mass, you could do that as well. All right, so let's say we have density of 2.86 grams per liter. We know that at STP, the volume is 22.4 liters at STP. Okay? Now, so what we got to find is the mass of 1 mole. That's what we don't know. So the way I like to do these is I just go ahead and set it up. 2.86 grams per liter. Actually, a better way to do that, you could write it like this. 2.86 grams per liter equals X over 22.4 liters. Okay? All right, so if you're given the density, then all you have to do is, you know, the volume at STP is always going to be 22.4 liters for a gas. You know the density because it was given to you. You got to find the mass. So we set it up. This is density. Remember, density is density equals mass over volume. That's a V, not no. All right, so we have density, 2.86 grams per liter, same thing as up here, equals X over 22.4. Multiply both sides by 22.4, liters cancel out. 2.86 times 22.41 is equal to 64.10 grams. Oh, let's just say grams. Okay, that's all there is to it. Now, another thing you might be asked to do is to calculate the percent of a hydrate. Hydrate is just a molecule with water molecules attached to it. All right, so let's say we had COF2 4H2O. Okay, so we need to do a couple of things. First of all, we need to find the molar mass of H2O. All right, so we know that hydrogen, actually we need to find the mass of everything. So let's just do that. So hydrogen is 1.008, and we have to multiply that by 2 because it's H2. Oxygen is 16.00. Fluorine is 19, and we gotta multiply that by 2 because it's F2. And then cobalt is 58.93. All right, so first thing we're going to do is we're going to add all of this up, right? And when we add all of that up, the molar mass of COF2 4H2O, okay, is 1.008 times 2 plus 19 times 2 in parentheses plus 16 plus 58.93. So that's coming up to be 114.95. Okay, grams per mole of this hydrate. Now, the other thing we're going to do is we have to find the mass of H2O, which is going to be 16 plus 1.008 plus 1.008. So that's 18.016, and that is the molar mass of H2O. Okay, hopefully you can see all that in the video. Ah, you can't, good. All right, now the question is asking us to calculate the percent by mass of H2O in the compound. So what we're going to do is we're going to take, similar to what we did before, we're we're going to have 18.016 divided by 114.95 times 100% equals, so 18.016 divided by 114.95, and that gives us wait, I forgot to multiply by 100. So that gives us 15.67% H2O. So of this mass, 15% is H2O. Okay? And so about 85% would be cobalt fluoride. All right? So that's percent hydrates. So this time we need to find the empirical formula. Now remember that the empirical formula, right? The empirical formula is going to tell you the actual number of atoms. So all ionic compounds like sodium chloride are empirical formulas. H2O is an empirical formula. C6H12O6 are empirical formulas. Okay? A molecular formula is, I think of it as being simplified. So for NaCl and H2O, those are already simplified. So that's the empirical and the molecular formula. But for something like C6H12, the molecular formula would be CH2O, because it's a 1 to 2 to 1 ratio. I mean, you could also have C3H6O3 or C12H24O12, right? And all three of these would have the same molecular compound or molecular formula. So that's the difference. Now, right this second, we want to find an empirical formula. So the question tells us that we have a compound that is 47.9% zinc, and it's 52.1% chlorine. So obviously this is going to be zinc chloride, but we've got to figure out the actual ratios, okay, or the actual formula. All right, so the first thing we're going to do is we're going to assume that we have 100 grams. Because if we have 100 grams, then this becomes 47.9 grams of zinc and 52.1 grams of chlorine. So from there, we got to find the molar masses. So we're going to look at the periodic table, and zinc, and as soon as I find it, pretty sure it's a transition element. All right, so zinc is 65.39 grams per mole, and chlorine is 35.45 grams per mole. So we do like we've been doing. We say 65.39 over, so nope, that's wrong. We're going to take the mass that we have, 47.9, divided by 65.39 times, nope, not times anything. All right, so we're going to multiply or divide that out. 47.9 divided by 65.39, and that gives us 0.73. And that's for zinc. And then for chlorine, we're going to say 52.1 divided by 35.45. So 52.1 divided by 35.45, that gives me 1.47. All right. All right. So now we're going to take the smaller of the two numbers, and we're going to say 0.73 divided by 0.73. This is for zinc. And we're going to take for chlorine 1.47 divided by 0.73. This is, of course, 1 mole. 1.47 divided by 0.73 is 2.01. We're just going to, and this probably should have been 0.46, so I just rounded when I shouldn't have. So that's 2. So that means, now these are our subscripts. So our formula for our empirical formula is going to be ZnCl2. All right, how do I know zinc goes first? It's the metal, okay? The least electronegative always goes first. All right, so then we have, so remember, molecular formula is telling you how many are actually in there. The empirical formula is reduced down. So these are molecular, but they're also empirical because that's what's there, okay? So then if we have something like ClCH2, and we know the molar mass is 98.96 grams per mole, okay, then we can figure out what we have. All right, so then we've got to find the mass. Now this is the mass of the molecular formula. So we're going to find the mass of this ClCH2. So chlorine is 35.45, carbon is 12, hydrogen is 1, but we're going to call it 2 because it's H2. So that would be 47, 49, 49.45. Okay? And so then we're going to take the molar mass, 98.96. We're going to divide that by the EMF, 49.45. So 98.96 divided by 49.45. And that should give us a whole number or something very close to a whole number. And so that tells us what to multiply that by. So we're going to take the ClCH2 and we're going to multiply each subscript by 2. So this would be Cl2C2H4. So then that would be the molecular formula for the 98.96 grams per mole.